Okay. Welcome back, everybody. So I just wanted to give you the kind of brief survey and motivation for what we're going to do this week and the coming 2 weeks. So this is actually what I think. This is my personal bias. It's one of the more interesting topics in classical mechanics. So this is where we're actually going to look at how we can solve a gravitational force problem or a problem with similar types of forces. And this is one of the few cases where we can find analytical solutions to the equations of motions of a system where we have two objects which interact with a given force. So we are going to look at some mathematical details, but hopefully that is going to allow us to reach this kind of glorious aims where we can get some deeper insight about the motion of objects under the influence of gravitational forces or similar types of forces. So if you take the Coulomb potential or the Coulomb force, the type of problem is going to be pretty similar to what you have here. So if you have a potential which depends on the inverse relative distance, if that's the type of mathematical form you have for it, you can just repeat all the calculations which we're going to do now and apply that to that specific problem as well. So there's a class of problems which are problems which can be solved analytically and which also give a lot of insight about the motion of objects. And this is essentially what we're going to do now. And for those of you who like astronomy and astrophysics, I guess everybody does, this is something which hopefully is going to give you some deeper insights about the types of motion you will see. So one of the things which we're going to explain is why do we have the perihelion, if you're familiar with that concept. That is about the largest or shortest distance which a planet has from the sun. We can explain the aphelion and many other properties of orbits for planetary systems, which also means that we are going to look at something which is called Kepler's laws, which some of you may have heard of, or many of you. So all these things are things which we can reach within some few lectures here. So let me just give you a quick overview of what we're going to cover this week and also in the coming weeks. So we need some technicality. So we need to define the two-body problem. And exercise 2 for this week is something which we are basically going to go through today. So many of the things with exercise 2 are things which you can reuse or which you will see derived here today. When we've done that, gone through these definitions, then we are going to prepare the ground for solving the equations. And we are going to extract an analytical equation, one expression, for the motion of an object around another object under the influence of a gravitational force. And then Friday, we're going to just solve exercises, discuss the homework. You should always feel free to ask questions, come back and forth with questions, and feel free not to be limited only by asking questions on Fridays. We have many office hours, so don't hesitate to actually use these office hours. Now, there's another thing which I did. I promised we went through some of the basics of solving differential equations with methods like these Runge-Kutta methods. This is something which we will not spend so much time on during the lectures, but you will find a video on that. There's similarly a video on Fourier analysis, which many of you will encounter in later physics courses and in mathematics courses. So there in that video, I'm just trying to give a kind of overarching motivation for why a Fourier analysis is a useful tool. So if you want to take a look at it, and I do appreciate feedback. I mean, it's definitely not Hollywood quality, but any kind of feedback is always nice to get. Okay. The kind of motivation for what we're going to do now is in this slide here. So these kind of two-body problems, they really play a central role in physics. It's not only life. I mean, to solve your own two-body problem can be very complicated. So half of the families, they divorce after some years. So that's a pretty complicated two-body problem. And solving two-body problems in general is something which gives us a deep, deep insight about the physics of many systems. It can be nuclear physics, atomic physics, gravitational problems, and many other problems. And the type of problems we are going to look at, they can easily be transferred to electromagnetism and a system like two electrons which interact via Coulomb potential, Coulomb force. So we are going to go through some technical, exciting steps. We are going to rewrite the equations in terms of the degrees of freedom of the relative motion and the center of mass motion. So the equation, when we start with the equations, if we want to deal with this system in Cartesian coordinates, and we are in a three-dimensional system, when you have two objects, you have 2 times 3 dimensions. So that becomes a 6-dimensional set of differential equations. So we normally say that you have the dimension of one object multiplied with the number of objects. And that's the complexity of the problem you want to solve. So by some nice transformations now, this sounds like a 6-dimensional problem, sounds like a pretty complicated thing. By some nice transformations, we're going to reduce the problem to a 3-dimensional. And then, since we are going to show that angular momentum is conserved, we can reduce this to a 2-dimensional problem. And we are going to get 2 uncoupled differential equations, which can be solved by themselves. So in principle, we are going to reduce, by some simple transformations, a 6-dimensional problem to 2 separate 1-dimensional problems. And that's simply because we're going to make a transformation of variables from what we normally call a lab frame, where you have particle 1 and particle 2, their positions, and you transform everything to the central mass system and the relative coordinates degrees of motion. By doing that, we're going to simplify the equations. And at the end, the reward here is that we are going to get equations which can be solved analytically. And with analytical solutions, we are going to interpret the physics. What does it mean? So that's the kind of basic outline of what is going to come this week and next week. So the advantage is actually that this allows us to extract physics insights, which we probably would not have gotten if we didn't have the analytical solution. Sometimes when we solve things numerically, we get a solution, but sometimes we would like to understand what does it mean in some simple terms. And this is what the analytical solution offers here. So physics is very much like this. We try to simplify a problem. We try to find the relevant degrees of freedom. And when we have the relevant degrees of freedom, we would like to have a simple picture of what is happening here. So that's the kind of, if you want to have an overarching take on it, this is roughly what is going to come now. And this is what you might say, in addition to harmonic oscillations, is perhaps a more interesting problem than these falling objects we looked at. Slightly boring problems, artificial potentials, which we had in the midterm. Now we are going to look at really how to solve real physics problems. Okay, so let's switch over to the whiteboard and take a closer look at the mathematics which we need to look at and some of the basic features which we are interested in here. So if you look back at the first midterm which we had, just let me quickly remind you of that. Then we had a part 3, or part C, I think we label it, where we had a potential like this. This was a 1-dimensional potential, and it was given by a 1 variable x, and it looked something like this, and then it had a linear term which took over when x went to infinity. The kind of motion which we found then, when we had an energy, we found that the energy was conserved. So the motion was then given by the energy, and our object would oscillate between these 2 values, back and forth. We could increase the energy, so we could be here, but this would still be a kind of motion which we would call a motion which forms a closed orbit. You would just go back and forth between two endpoints. So there would be no change. I mean, life would be extremely predictable, just from one point to the other one, back and forth, all the time. So this was the one-dimensional problem. And this is an example of a potential. We have a motion which is confined within this potential web. Now, what happens now, when we go to the two-dimensional case, so this was in one dimension. If you go to two or higher dimensions, what we are going to do now is to plot the potential as a function of the spherical radius, or if you have polar coordinates, this is going to be the radius. So that means that the radius goes from 0 to infinity. And we are going to find a potential in this specific, with this specific degree of freedom, which is going to look something like this. This is with a gravitational force. So when V of R is proportional to something like -1 divided by R times some constant, which we just call for gamma here. So this could be the Coulomb potential, it could be a gravitational potential, or it could be any other type of potential which has this physical shape. But there is more here actually. So I say this is proportional, because when you plot that one, it's not going to look like that. So there's more to the picture than meets the eye here, which we are coming back to. Now, the motion which we are going to have now, so if you place yourself down here, this motion is going to lead to circular motion. When we place ourselves at a higher energy, but we are still confined to move in here, this is going to be something which results in elliptical motion. And we are going to see that pretty soon. So both these cases are cases where we have a confined motion. So you're confined to move in a specific orbit around something. So this is normally what we would call a confined motion. Then, if we place ourselves here at this energy, suppose this is the energy which we have, this is going to lead to something which we are going to call a parabolic motion. Then we can place ourselves here in energy. So these are the energies. So if you go back to what we did in the midterm and some of the exercises before that, when we drew these lines, we said that this corresponds to a specific energy. And that means that you're oscillating either back and forth. The line at the bottom is going to correspond to circular motion. Then, if you now have an energy which is larger than 0, so we're assuming that this has an energy scale where this is 0, this is going to be called the hyperbolic motion. Now, when we are going to plot this in terms of real objects, the way you could think of that, if we now look at a possible way to visualize what we have. So suppose we have the sun here. So this is your sun. And then the hyperbolic motion is an object which comes in. It feels an attraction due to the sun, but then it has enough energy to escape from the sun. So that means that your motion is going to look like this. So this is the way this motion is going to look like if you want to plot it in a two-dimensional plane, where the sun is the attractive body. So you have something which comes in. It could be a comet, it could be something else. Then, if we now look at the confined motions, if we take the blue lines here, that means that you would have something like this, just goes in circles around. So just imagine that as a circle, right? I mean, you see, my drawing skills have always been limited. Just think of that as a circle. Then the parabolic motion is also going to be pretty similar to the hyperbolic motion. So all these kinds of insights is something which we can derive by looking at the analytical solutions which we're going to get. And that's pretty powerful. At least I think so. So this is a thing you can impress your friends with on a Friday party when you have the solutions. And maybe that's the reason nobody invites me to parties anymore. I couldn't resist. Anyway, this is actually, I think to me, this is one of the first, for me, when I saw this, was one of the beautiful demonstrations of how powerful the mix of physics and mathematics is. But let's try to go through the details now. So these are the kind of things which we're going to derive. And let's now bring in the basic elements. So we need some technicalities. So we have a technicality here. So the first thing we are going to do now is to define the central mass motion. And the relative motion and relative. So we're going to stay with a two-body problem, but there's nothing which hinders you to extend what we are doing here to many objects. So in the second midterm, which we normally have, I mean, the second midterm has been one of the examples which we have used is to actually write a program for the solar system. And in that case, you will need to add more than just two objects. But let's now stay with only two objects. So we are going to define the central mass motion. So this is the C of M, or the central mass coordinate. And that's something which we are going to define as an M1. So this is a weighted position. So we have two objects. And this is divided by the total mass, M1 plus M2. And we are going to define M1 plus M2 here in terms of the total mass, M. We need the relative coordinate. And we are going to write that one as in terms of R1 minus R2. So if you have two objects with the same mass, this obviously simplifies to 1/2 times R1 plus R2 if they have the same mass. But we are going to assume now, for the sake of the generality, we are going to assume that the masses are different. You can then manipulate these equations, and this is something which we probably saw in physics 183. We can rewrite R1 in terms of the new coordinates. So this will be given by M2 divided by M, multiplied with the relative distance, and R2 is equal to R minus M1. So these are just simple manipulations. Sorry, it's not R1 there, but just R. And divided by M. So there is one important thing now, is that the potential, when we write it, is going to be a potential which now depends on the relative distance only. Most of the potentials which we encounter in physics, they depend only on the relative distance between two objects. So it means that this is given by V of the absolute value of R. And R, in our case, is now given by R1 minus R2. So if we are in 3 dimensions, it means that R of I is simply xi times I plus yi times the unit vector in the in the y direction, plus z of I multiplied with the unit vector in the z direction. That means that the absolute value of R, which we are going to write as just R, is given by, in our case, when we have two particles only, x1 minus x2 squared, plus y1 minus y2 squared, and there is a plus here of z1 minus z2 squared. So the potential in many physics cases, which you're going to encounter later as well, depends normally only on the relative distance. That has quite some interesting consequences for us. So obviously, one of the things is that this potential is translationally invariant. So if I change R1 and R2 by the same quantity, so I just shift my coordinate system, then the potential is left unchanged because I would have a potential which depends only on the relative distance. So if I change R1 with a constant 10, and I change R2 with a constant 10, then I take R1 minus R2, I have 10 minus 10. So the argument is unchanged. So this is called translational invariance. I can translate the system by a constant, and the potential takes the same value. So that's an important symmetry in many physics potentials. The next thing we can do now is to look at the linear momentum. So in our case, the gravitational potential, if we now want to write it out properly, if we take and write the gravitational potential, this is a V of R, and it's given by the gravitational constant, and then I have the mass of the one object times the one of the other object, and this is simply divided by the absolute value of R1 minus R2, and we typically just write this as minus G of M1 of M2 of R. So when I use a lowercase r with no subscript, that is always the relative distance. And if there is no vector, this is just the value of the relative distance. Any questions so far? I promised you many exciting definitions today. So we need to establish some of these definitions in order to simplify the equations. And basically what you're going to do here is something which is pretty related to exercise 2 in the coming homework, which we have now on Friday. Okay, so let's continue along these lines. If you want to make a graph here, you could now think of you having some origin. And then you have an object 1 here. And you have an object 2. And then you have the distance from the origin to R2 to object 1, the distance here. And then you would have the vector R, which is simply the relative distance between R1 and R2. Now, one quantity which we can start looking at is something which we would call the total linear momentum. So the total linear momentum, as we defined it just some time ago, that was in the very beginning of the semester, would be now a sum over all the particles we have. And we're assuming that the masses do not change. This is pretty common when you're dealing with Newtonian mechanics. You make an assumption that the mass of the objects do not change. That's a pretty common assumption. So that means that if you take the derivative of the mass, that's equal to 0. The time derivative. That means that then we have a d of Ri of dt, which again means that when we now look at this, if I look at the definition of R, which is given by M1 of R1 plus M2 times R2 here, divided by the total mass, if I take its derivative of d of R dt, this is simply 1 over m of the sum of I equal 1 to 2 of M1 of mi actually. So this is I of d of Ri of dt. And this quantity which you see here now, if I now multiply away m, so if I multiply with m on both sides, what I get then is that I have m of d of R of dt, and this quantity here is nothing but the total momentum. So this quantity becomes equal to, if I multiply away, then I have that m of d of R dt is equal to P. Now let's look at an interesting case now. So we know that if I look at the force, if you now go back to what we did in the very beginning of the semester, we know that this net force in this specific system is actually given by the derivative of the total kinetic energy with respect to time. So if I look at the expression which I have here, this is the same as the mass times the second derivative of r, the central mass coordinate. Now, you could actually do something pretty intuitively. Suppose now that your potential V of r, so you don't need to do any calculations, but then later we are going to show that by calculation here. So suppose that does not depend on r, on the central mass coordinate. This is pretty common actually. So the gravitational force is an example of a potential which does not depend on the central mass coordinate. So that means that if I now take the derivative of this potential, and I'm going to write it, take the gradient with respect to r, of V of r, what should I get then? 0, right? So the consequence here, suppose now I'm looking at, so this will be the force, right? So this is the force as a function of r. And I know now that if I take the derivative of the momentum with respect to t, I should actually get now, what I see now is that this means that dp, the total linear momentum, has to be equal to 0. Would you agree upon that? So if there is no dependence on the center of mass motion, then the linear momentum, the total linear momentum, its time derivative has to be equal to 0. And that follows simply from the fact that the force, the net force, as a function of r is equal to 0. So what does that mean for us? This has some important consequences when we're now going to simplify the equations. But it means also that something is conserved, right? If this is the case. So which quantity is conserved here? Yeah? Linear momentum is a conserved quantity. So the total linear momentum, not the relative linear momentum, but the total one is conserved. This means, if you now go back to the equations which we have, if you look at this equation here, if you now take this equation, so this is nothing but the acceleration as a function of the central mass coordinate. And when that force is equal to 0, that leads to a trivial equation, right? Because it's a second derivative with respect to t, which is equal to 0. And we know how to solve that equation, right? We know that if we integrate a derivative which is equal to 0, that just gives us a constant. So what we would say then is that the motion in the central mass coordinate, degree of freedom, can trivially be solved. So this already says that the problem, the original problem, which is a 6-dimensional problem because we have 2 objects in 3 dimensions, has now been reduced to one problem, which is a 3-dimensional problem because we have the x, the y, and the z component of the central mass coordinate. This can be trivially solved because its second derivative with respect to time is equal to 0. So in a sense, what we have done already is to anticipate the kind of discussion we're going to end up with, is that the original problem, which had 6 dimensions, 2 particles times 3 spatial dimensions, is something which we now can reduce to a 3-dimensional problem. So the central mass motion can be trivially solved. And that's simply because we have the acceleration here, which is equal to 0. So let's write that down. And let me also show you this in a slightly different way. So this follows if you have a potential which depends only on the relative distance, then we will always have this result. So if we look at what we have, we will say that the acceleration for the central mass coordinate, which is this d of r dt, the second derivative, this is this quantity. So what we have is that m of r is equal to 0, and that can be trivially solved. We could view this in a different way. So if we now have a force, assume now that we have two particles, just to simplify things, n equal 2, and internal forces only. So there's no external force which is applied to the system. Then we know that if I calculate the net force, that is the force on particle 1 plus the force on particle 2. In our case, the force on particle 1 is going to be a force which depends on particle 2, the relative distance. So this is our gravitational force in this case. And then we have plus an F21. And we know from Newton's third law that F21 has to be equal to minus F12. If there is an action on something, there's a reaction. And these forces have to be opposite. So that means simply that this has to be equal to 0. So typically, when you have a force which depends only on the relative distance, this is a situation where you are dealing with internal forces only. Because now what you have is something which depends on a distance between the two particles. Now, if that is a situation, then you can say that my problem now reduces simply to a problem where we need to deal with the degrees of freedom of the relative motion. The central mass motion can be trivially solved. Any questions? Does this sound reasonable? Yeah?
Just to clarify, so when you say center of mass motion, you mean motion about the center of mass?
Yes,
okay.
Yes. Okay. So you can think now, what we are doing now, we have two particles, right? So you could write the equations in terms of R1 and R2, the two particles, right? So if you're dealing with 3 dimensions, particle 1 would have an equation in the x direction, in the y direction, and in the z direction. And the same for particle 2. That would give you 6 coupled differential equations for the acceleration, which then reduces to velocities and positions, like we did before. Now, if you now look at the system, instead of R1 and R2, you rewrite it in terms of the center of mass motion and the relative motion. The system simplifies because the force depends only on the relative distance. This is something you will see again and again in physics. So if you have a system like this, then you can simplify it immediately. The calculation procedure becomes much simpler. So what we are going to end up with now is three degrees of freedom, but we are going to see that angular momentum, due to the fact that we have a force which conserves angular momentum, we are going to reduce the equation to just 2 equations, 2 differential equations. And these equations are going to be uncoupled. And that is what allows us to find an analytical solution of the gravitational problem. Yeah?
What exactly do you mean when you say uncoupled?
So if you think back to what we did let's say this is a good question actually. So suppose now we took the equations for the harmonic oscillator, the simplest case, minus k times x. The way we typically wrote this would be now for an equation with the velocity, which is equal to the acceleration, which is dx dt, and that's equal to minus k of x. And then we rewrote it in terms of another equation, dt equal to v. Now, these equations here, you see now, these are called couple equations because v here, this equation which you see here, depends on x here.
Oh, I see.
So these are couple. If you go back to the gravitational problem, in the gravitational problem, when you did the Earth-Sun problem in homework number, I think it was 4 or 5, you had 1 over the relative distance cubed, and the relative distance depends on x squared plus y squared. So x and y depend on each other. And then we say that the differential equations are coupled. So you cannot, if you can separate them, then you can find an analytical solution immediately, because then you can solve the equation for one and the equation for the other one without linking them. Whereas when you have this equation for the harmonic oscillator, the equation for V depends on X. So that means that we need to solve them in a coupled way. So this is normally what's meant with coupled differential equations. If you can decouple things, then you end up with simple differential equations, which you often, if you're lucky, you can solve analytically. And this is what we're going to do now with some simple transformations. And that's why I'm spending some time on this, because I think it's important to have this clear, because that allows you to see the wood for the trees. Actually, that saying, when I was a kid, I never understood it. What does it mean to see the wood for the trees? I really never understood it before I was a grown-up. Okay. So let's continue a little bit now. And what we have, if the net force in the central mass direction is 0, then we have 0 acceleration, and then we can solve things trivially. Let's now look at the relative coordinate, or the differential equations for the relative motion. So you will often see this being used as a kind of name for what we are going to do now. So we have decided that R, this is the way we defined it, is given by R1 minus R2. In more general terms, you will see something like this, Rij, which is now given by the difference between Ri minus Rj. We are going to stay with 2 particles only now. This means that if I take the second derivative of d of r of dt, this is obviously the second derivative of r1 dt minus the second derivative of r2 of dt squared. We know that this is the acceleration. So this is something we would call A1 minus A2, right? The second derivative with respect to R is the acceleration. And this is something which we again can rewrite as the force acting on particle 1 from particle 2 divided by the mass of particle 1 minus F21 divided by M2. Would you agree upon that? Now we are confining ourselves to internal forces only. Then what we have is that F21 is equal to minus F12. That follows from Newton's third law. So we can then rewrite things in terms of an F12 of 1 divided by M1 plus 1 divided by M2 here. And then it's pretty common now to introduce this, and you've probably seen that back in physics 183. It's common to introduce this reduced mass, which is M1 times M2 divided by m1, the total mass, m1 plus m2. You would see this in another disguise, written like this, divided by m. So I can now multiply with m on both sides, the total mass here. So you can see now if I just rewrite this equation, I can rewrite this in terms of this term mu multiplied with the second derivative of r of dt, and this is equal to the force 1, 2 here. And this is now my gravitational force. So if I want to summarize what we had for the center of mass motion, we found that d of r of dt, second derivative, is equal to 0. And these are the equations which we now need to solve. And if I switch to the gravitational force, so we can actually rewrite this as a mu times a for the relative motion equal to F12. And if we want to specify this to be the gravitational force, this is the same as minus g times m1 times m2 multiplied with the relative motion, the vector, divided by r cubed. And we can now, if we now look at this equation here, we can now get rid of mu. So we can rewrite that one. We can then show that a of r is then equal to minus g times m multiplied with r divided by r cubed. And m is the total mass of the system. So this is a very interesting statement, because what it says is that the acceleration depends on the relative motion or the relative position, the second derivative, and the trajectory depends on the total mass only. So this is just a simple manipulation. And then we have the next equation, which says that the acceleration for the linear or for the central mass is actually given by 0. So when I say that I have reduced the problem to a 3-dimensional problem, this is actually what it means, because we still have to solve the equation for the central mass, but this is trivially solved because it's just to integrate up 0. And we should know how to do that. Okay. So the next thing we need to look at now is conservation of angular momentum. And that's going to be a little bit more interesting here. So let's look at angular momentum. And now comes a very important definition, which you will meet again and again in physics. There is a frame which we can define. So we call this the center of mass frame. So this is the center of mass frame. So think of you now redefining your origin. You can always redefine your origin. Remember that what we said with these forces is that these forces are invariant under translations. So I could change my origin now so that the central mass value R is simply defined to be 0. There's nothing which hinders you to redefine it. You can always redefine what is 0, what is your origin, as long as the forces have some specific symmetries. So if I translate my system so that the central mass position is equal to 0, this has no effect on the value of the potential. So that's a freedom which we can use. And you are going to encounter, if you're going to do particle physics, or you do nuclear physics and you're looking at cross sections, when you derive the equations for that, for scattering experiments, This is the way we actually get insights about the physics, by bombarding things against each other. And then we see how they scatter. You can always define everything in the central mass frame. So what we're doing then, we simply put the central mass coordinate to 0. That's just our new origin. And that's the central mass frame. And that's going to simplify a lot of the numerics. So this means that we just define the central mass R to be equal to 0. So you could now think of this as your origin. And then you have a particle 1 here and a particle 2 here. So you would have a distance here, an R2. And then you have a distance here, which is R1. Now, this obviously simplifies life a lot. So what I get then is that since the central mass is equal to 0, I get that R1 is m2 divided by the total mass times the relative distance, and R2 is equal to minus m1 of R divided by m. So what we're going to do now is to calculate the angular momentum in this frame. And if you look at the angular momentum, this is something which we defined in the beginning of the semester as the vector which is orthogonal on a plane which is spanned by the position R and the momentum. So this is simply given by R2 times P2 here. And what comes now is a basic exercise in just inserting the equations which we have here, and small manipulations, and some of the manipulations involve the linear momentum. So the momentum for particle I is given by mi times the time derivative with respect to the derivative with respect to time. So this is just the momentum. So I'm going to put in this equation here, and this equation in here, and in here. And then I'm also going to use the equation for the linear momentum for each particle in the same equation. So that means that what I get then is the following. When I just bring everything in here, so I find that the angular momentum is now given by m1, and this has r1 times the time derivative of r1 dt plus m2, and then I have r2 times, so no, not times, but it's the cross product dt. So these are cross products. And then what I'm going to do now is to put in the expressions which we have here. So I'm going to take these expressions and plug them into the expression for the R1 and R2, both the derivative and the vector itself. So what I get then is that this becomes equal to, and we are getting close to the end here. So this gets equal to m1 times m2 divided by m multiplied, cross product with m2 of m, and then I have the time derivative of d of r dt, and then I have plus, and since I'm multiplying two negative values, minus m2 divided by m, then I get a plus, and then I have an m2 here, and this is given by r cross m2 of m of d of r. This should actually be m1, sorry. I was a little bit too fast here. This is actually m1 of d of r dt. And this is nothing but mu, the relative mass, as we called it, or the reduced mass of r times the time derivative of the relative position. And what we also know is that if we now take the second derivative of d of r, so we had that a of r times mu is the same as mu of d, the second derivative of d of r dt. This is equal to the force. So what I'm going to do now, and this is the last thing we do today, we are now going to calculate dl dt. And we are going to see that this one, and this is where we will start on Wednesday, we are going to see that this is equal to 0. So I leave that as a small teaser to you guys before we leave now. I'm going to pick it to start there on Wednesday. But this is an important thing because it means that the angular momentum is a constant of the motion. The angular momentum is perpendicular to r and momentum, which means that we can look at the motion in a plane. And then we get rid of 1 additional degrees of freedom. Okay, thanks for coming, guys. Right? And then we meet again on Wednesday. Feel free to hang around if you have questions about exercises or any other thing you'd like to ask about. For those of you online, I'm going to stop the recording.